Hey students, thanks for joining. Today we'll be introducing from where we have finished in the last class, and that is the error. We have finalized the slide in the last class, so we'll be moving to the next slide. And as you can see from the slide, the new topic we will be beginning today, and that is the system of linear equations. As you can see here, we will be learning what is the system of linear equations. By this time you have learned this thing, the system of linear equations, as well as you have solved these things as well, not only in these engineering studies but also in your intermediate level, or also I can say from your primary level, or at least the higher secondary level, or the secondary level. You have learned how to solve the system of linear equations. So we'll be reviewing all those things here in a accumulated way, as well as we will be also learning here some new techniques which will be introducing our needs and showing us the path how we can derive a logarithm, an algorithm which will be available for the computer to solve the multi-purposing task. That is, if we want to solve numerous amount of system of linear equations to get the solutions of a high number of unknowns, then how we will be using the computer to go through and give us the solutions. I will be giving you the examples as well, which will make you comprehensive to understand as well. But before that, I will be asking you, do you know what is the system of linear equations? What is equations? You know what is equations. And what is linear equation? If I ask you, can you give me the explanation of the linear equations? If I ask you, well, we see here, say for example, if I give an equation like this, 7x1 plus 9x2 is equals to 2. Say for example, this is an equations, or 20 if I say. This is an equation. So this is an equations, and as you all know that these things, as it is given there, all these things are nothing but the variables. We say this one is variable, and also this one is a variable. So what is variable? The values of which can vary, and we need to determine these things. That's why we say this is variable, and obviously these things are unknown variables. And to solve this, to make it known, we solve the linear equations. And why do we call this is an equation? First of all, no doubt about that, this is an equation. But secondly, we'll have to say what is the purpose, or why we'll be calling this as a linear equations, and what is non-linear equations. As if you can remember that in the last class we have given example of linear equations, and also we have said what is non-linear equation. The linear equations is linear equations will be in which we will be getting the if we plot the data in the graph, not the data, the equations in the graph, then we'll be getting a linear linear shape of the graph. That is, if we plot this in the graph, we'll be getting, you know, a linear equations like this or that, whatever this is. All these are linear equations. So straight line will be getting for two variables, as you can see here, given. So one in the variables will be plotting in one axis. This one may be x1 and this may be x2. This we say one is dependent and one is independent, and depending upon which we are using in which purpose, that is our main concern there. But however, this is nothing much important while we will be solving our linear equations, and there might be multiple numbers of variables, as you know, not only the two. I am giving just example of two for your convenience, so that we can expand our knowledge later on, so that you will be able to understand the higher order, or not only the nonlinear but also the multiple number of variables, more than 2, 3, 4, 5, or many of that. You can easily understand after that. And that's why I'm giving the example of two variables here. So now I'm coming to the point that as this will be giving us a straight line, in the graph, or straight shape of the graph within the graphical representation. And that's why this linearity, that's why we call this as linear equation. And in this case you will be able to understand that the variable will have the power. If I say it will be 1, that will not be true, accurate in 100% case, just because not always necessary that you will have to make sure that the power of this will be 1. It is not necessary. Rather we say that the we say this, the linearity is there. That means the whatever we use here, it will give you an straight line or linear type of graph. That is the most important thing. Or in other way you can also say this, it will be only possible when the power of variables will be 1. Then it will be only possible. Unless it is 1, if we use just one unknown, 7x1 equals to 3, for example, in this case this is possible that what we say, it will be possible. Also this will be possible in case of two variables, like say if I say this is 7x square equals to 3, we can, you know that you cannot plot this in the graph. For 2D example, two-dimensional graph and two variables, I give the example here. You see x2 or 7x2 equals to 49x1, x2 square equals to 49x1, as you can see here. And from this we can, and this will be x1 square, see here. So from these equations, can you say whether it will be linear equations or non-linear equations? Well, in this case we must assume one as the dependent variable and another one as independent variable, so that we can plot this in the graph. So if we assume that this is the dependent variable, this is independent variable, then we will be getting the values of x2 as plus minus something. And that's why this will be, if we plot this, we'll be getting a graph like this one. And this is also linear graph, as you know, you can see here. So this is also a linear. So in this case also we are watching there, the power is not the value of 1, unity is not there, but that is the true thing, that the power of this two of these variables are equal. So not always, if I say that if the power of this 1, that will be the linearity, it will be the determiner of the linearity. That is not the true thing. Rather, the true thing is that whenever you will be using multiple number of at least two variables, whatever it is, the linearity means that whenever we'll be plotting it in the graph, it will be representing a straight line, or the linearity it will be showing in the graph. So now come to the point, what will happen in case of three variables? In case of three variables or multiple variables, whatever we say, so for example 7x1, 9x2, ABC also can be there, or XYZ also can be there as variables. You know, this all are variables, nothing else. So we can represent it in any way, either way, it doesn't matter. However, x3 equals to 2. This is an equation. This might be 2, 0, whatever it is, it doesn't matter. Okay. So three variables are there. So how to understand the linearity? Obviously, we'll be understanding the linearity very easily if the power of this tree will be equal, and that should be equals to 1, as you know. So as it is, so we can say that this is a linear equation. And how we can say this is linear equation? What will be the graphical representation? In graphical representation as well, in this case, this will be representing a straight line. If these are three axes, say x, say y, and say this is z, and the straight line for this maybe as it is shown here, there might be a straight line like this, and this will be a straight line, not a curve or anything else. And also this will not be a straight line, actually this might be you know, a 3D thing we'll be getting there. A 3D shape might be obtained from this particular equation. That is also possible, but whatever it is, it will be linear in properties. That is our main concept. So whatever we'll be getting, and if we use multiple numbers of also up to 3 equations, we can graphically represent this thing. If it is more than 3, and also 3D representation is very tough for you to make it visualize in your script. But if you go more than 3, as we don't have the understanding or visualization of 4th dimension, that's why we will not be able to represent it using a graph. That's why we'll have to go for another solution. So this is the first thing we'll be discussing afterwards, that is different methods of or techniques of solving linear equations. The first one will be the graphical one, as we are showing this in graphical representation while introducing the topic as well. However, we'll be discussing it afterwards. Now come to the point. What is the significance of these variables? In mathematics you will be learning these things, that these are the variables, but you will not be knowing or learning the applications. But maybe you will be learning as well from now on, just because we are going for the Abbott manual, where practical examples are emphasized for the students, so that it will be very comprehensive to you for understanding. However, that doesn't matter. I am just now raising the point that what is the purpose of using these variables? Why? You know, sometimes we know this, some variables are acting for after this. When you will be conducting the research in the final year, you will be also using these variables. You will be playing with these variables, if I can say, and this is the fact that you will be working with these variables to get the values or the appropriate values for these variables. So what are these variables actually? These variables might be if I give example of the analytic mechanics you have learned in the last year, the first year you have in your civil engineering courses, there was a problem, or multiple problems were there, where you have obtained different reaction values, RAX, RAY. These things are variables, you know, and these things are variables, and from these variables you will be solving. There was an equation for using these variables, like say 7 RAX plus 9 RAY equals to 2. This was an equation, as you know. So there might be another equations, like to solve this thing, how many equations will be needing? That is my question, first question. Obviously you will say that for solving these things we will be needing at least 2 number of equations, just because the number of unknown is 2. And that's why we say the static equilibrium equation for 2D, we know summation of fx, summation of fy, and summation of m equals to 0. So we have 3 equations, so we have 3 unknowns to solve from there, as you see, 7x, 7 and 9ay. And if I have another say rbx, so that's why we are using simply supported beam, so that we will be getting 3 unknowns reactions from there, so that we can solve it easily. That's why the 3 equations, as it is known from the static equilibrium equations, that's why we use the simply supported beams. And even if we use multiple more than these 3 reactions, then what we do, we give an internal conditions, an internal hinge at a point, so that you can understand that the moment at this point is 0, that will give you another equations at this point, say md equals to 0. This is another equations and or the support for use so that you can solve this. Unless that if we give this example with say 2 hinge, or we give it with the number of reactions which will be greater than 3, you will not be able to solve this thing, you know. So that's why we need a number of equations which will be equal to the number of unknowns to solve any problem. Say for example, if I ask you 7x1 plus 9x2, the example we have given above, so x3 equals to 0. This is an equation. Can you solve this x1, x2 and x3? Yes, you can solve this, but this will not be any reasonable, a particular solution will not be obtained. Multiple number of combinations might be obtained from these three equations, so that you will be very much confused with these three variables, which value is to be used and which one is not to. So say for example, if I give with this 3 and one equation is only there, so what will be the solution? There will be numerous number of solutions. So if Rax might be 10, Rax might be 1000, and many more number of values is possible. So which value will be counting while designing the structures? So that will become very confusing for you. So you cannot go further using only this particular information. So you need more information to solve this, and that's why we say, even if I ask if it is possible, if we have 2 equations for these 3 variables, even then it will be impossible for you to solve this. Impossible for you to solve this, the x1, x2, x3. Still there will be multiple number of solutions you'll be gaining, not a particular set of equations will be particular set of variables will be getting. You will be getting multiple sets of equations, so that's why that will be still confusing. And what will happen if we use 3 number of equations, in this case x1 say minus, so we can say 0 is the coefficient in this case, so we better omit this thing. So for example, minus x3 is equals to 5. Say this is another value. From now on, as it is 3 equations, as you can see, as you can easily solve this thing, and you will be getting only one set of equations of x1, x2 and x3 from this particular sets of equations. So that's why we say the number of unknowns must be equal to the number of variables in a particular set of equations to solve the system of linear equation. So that is our main concern while solving system of linear equation. And even if I ask you that if I increase one number of equations there, one number of equation, if I add here, say for example 5x1 minus 2x2 plus 3x3 equals to 9, then what will happen? If I increase this thing, this will also become unstable. Just because of what? Just because you will not get any particular set of solution from these 4 equations unless all these 4 are consistent equations. That is, I have given all these 4 equations without any prior data or value or any exact combination of x1, x2 and x3. So as I don't know any value of x1, x2, x3, and I'm just giving the equation, so when I am giving 3 equations like this, you know that you must will be getting a particular set of solutions, x1, x2, x3. One particular set of solutions you'll be getting from there. But whenever I'm adding another thing, you will have to make sure whatever the value of x1, x2, and x3 is, and that values will be also going in line with this equation as well. Unless this is possible, then these four equations will not be consistent, and most of the cases that happens. That's why you will not be getting a particular set of solutions from this four number of equations. So in general, that's why we say, as it will not be consistent, the value of x1, x2, x3 in most cases and almost all the cases. That's why if you increase number of equations, that is also problem, and also if you diminish the number of equations, that is also problem. So what will be the solution? The exact number of equations should be equal to the number of unknown variables we are using for those equations. That is the only way, so that you can get a particular set of solutions from these equations. So that is our main concern here. Unless the consistency, I have said, I have explained this thing. I hope you have also understood this. So I'm better I don't go further in this concept. So first thing, the most important thing we have learned here, that is the number of variables we're getting here should be equals to the number of equations for solving a linear equations. Now we'll be going for the concept. Let's move to the slide again. System of linear equation. If I say that the system of linear equations, a system of equation is when two or more equations working together. There are different methods to solve system of linear equations. I have given some examples, and some are made in bold, so that we will be giving examples of that in our course. And there are other techniques as well. As you can see, graphical method, Cramer's rule, naive Gauss elimination, Gauss-Jordan, Gauss-Seidel, etc. So different techniques are there for solving system of linear equations, and some limitations are there behind each technique. So we will be learning those, which will make us to understand how we'll be using our computer, how we can use our computer to go through to solve those linear equations, which will give you the basics of numerical techniques here. This is the difference where we are distinct from the mathematical courses, that will be giving you an indication how you can go through and how to use your computer to solve any problems using numerical methods. So graphical method, the first thing. The graphical method, as you all know, I have already discussed. The graphical solution is the way of plotting the equations in the graph and detect the intersection point to obtain the solution. This is the thing which we need to understand, that in linear equations, system of linear equation, we know in 2D, if we use two variables, the graphical solution will be like this. And whenever we'll be plotting this, the two straight lines from two equations will be there, and those two will be intersecting in a point, and graphical representation will be giving you a good value of solution, a particular value x1 and x2. So for two equations, you know, two variables will be there. So exact number of variables and exact number of solutions should be there for any solving any so system of linear equation. However, we'll be giving an example which will make us easier to understand here. We'll be watching a problem, how to solve a graphical solution. The question I will be importing here now. I'll be importing the question. We'll be using a graphical. So we'll be using a graphical solution to solve these two equations. As you can see, hopefully you can see, the question. It says that use graphical solution to solve this two. So what is our task? If in the exam you see this sort of questions, that will be very much easier for you as well. It is needlessly I'm explaining, but still let's see. This is the graph we'll be getting, or the graph you will be getting is this one. So you need graph papers for solving this. Then we'll be plotting the straight lines. Say 3x1 and 2x2 equals to 18. So how to plot this in the graph? First of all, you must need to get some points for this particular solution. So you must need to understand the points where this will be intersecting. So from the first equation, we need 2 points so that we can plot a straight line. The first point will be for 3x1 and 2x2. If you make the point like, if you say x1 is 0, x2 will be equals to 9, x1 if it is 0. So 1 point we are getting x1 equals to 0. This is x1, say, and this is x2. So say this is x1 equals to 0 and x2 equals to 9. So this will be a point 9, say, so 0 comma 9. And another solution, if we make x2 equals to 0, x1 will become 6. So the next point will be this one, which will be 6, 0, we can say. So tentative points are there. So using this one, we can easily draw a straight line, as you can see. So this will be the straight line going through this. Okay. Now we say another from this equation, this will be another straight line. So if you use x1 equals to 0, x2 will become what? If x1 equals to 0, then x2 will become 1, as you know. So it will become 1. So 0 comma 1. And again, if I say the x2 equals to 0, then x1 will become minus 2. So minus 2 comma 0, that will be another value. So using this 2, we can draw another straight line here, as you can see. And these two straight lines obviously will be intersecting in a point. That is our point of concern, this point and this point from the graph. This is nothing but, as we have said, this was 0 comma 9, this was 0 comma 1, this was minus 2 comma 0, and this was 6 comma 0. So from these two straight lines, the intersecting point from the graph, you will be able to understand the graph will give you the value of 4 comma 3. So we'll be saying that this is 4 and this is 3. However, so this value will give you x1 comma x2 only one set of solutions, that is 4 comma 3, and that is our answer for this particular problem. So graphical representation is very easy to think about. So let's now move to the slide back again. What is the problem? Graphical depiction of singular or ill-coordinated systems. So not only the problem is that whenever we'll be going for 3D instead of 2D, that will be creating problem for us, or above 3, it is impossible for us to represent using the graphical representation to solve any system of linear equation, as you know. But still then, even if it is a two-dimensional problem, sometimes that might create problems where there are three depictions are given. First of all, no solution, say this one. So you will be getting no solution at all two parallel straight lines will be there, and from there you will be not getting any particular solution. That will be creating a problem for graphical representation, and also problem creating from all the techniques, just because there will be no any particular set of solution is possible here. So whatever. This second thing, infinite solutions. The two straight lines are the same thing, as you know, as you can see from this particular two equations. Minus half x1 plus x2 equals to 1, minus x1 plus 2 is x2 equals to 2. These two are basically the same equation, so we will be getting infinite number of solutions from this, just because in each point it will be intersecting each other. The two straight lines are identical, that's why we will be getting infinite number of solutions. That is also problem. Okay. And third thing, that is the most important thing, why you will not be most of the time will not be giving focus on the graphical solution, although you will be going for graphical solution in most of the sessional courses you will be conducting later on in the civil engineering program. But still, then see why we don't give focus on graphical solution, unless even if we give emphasis on in graphical solution, we say the approximate value from your eye judgment. These things, these are similar sort of words we use while using the graphical representation or solution. However, the thing I have mentioned here, the ill-coordinated system where the slopes are very close, that the point of intersection is difficult to detect visually. So think about these two graphs, and these two straight lines, as you can see from this number C figure. These two straight lines are not parallel, neither these two twos are identical as well. So we'll be getting only one solution, that is true. But the problem is, as the slopes are very close, so the the intersecting point which we'll be getting, it will be very much impossible to understand. So very tough task for you to identify the intersecting point. That's why the graphical solution will be moving from graphical solution to another form, another technique, and that is the Cramer's rule. This is very well known to you. I don't want to give any introduction with this rule, as you all know about this rule. So one thing just I want to say, that we will be able to solve as much equations as we want using this Cramer's rule. Only the thing, again, you have to remember that the number of solutions number of variables should be or must be equals to the number of, the number of variables must be equals to the number of equations in all cases while solving system of linear equation. Unless this is the equals, these tools are equal, will not be able to apply our technique. So first and foremost thing is to identify or to justify that whether these tools are equal or not. However, the Cramer's rule we can use for solving multiple number of variables, as much variable as we can. The technique is in simple form. I can say, if I can rewrite this in matrix form, we can write it like this. A matrix, A means A1, A2, A11, A12, A13. As you can see, within the matrix all the coefficients of the variables are included there, and X is the set of variable. We say this is the variable vector, and B is another vector. We say this is the scalar vector. All these B1, B2 and B3 are the constant terms which we use in the remaining portion and in the opposite side of the equation. That is the set of B1, B2 and B3, the scalar vector. Using this tree we can solve the Cramer's rule. First says what we need to determine the determinant of the coefficient matrix A. After that, we in each time whatever we are trying to solve, we'll be going for, say, whenever we'll be trying to solve x1, we will be replacing the coefficients of x1 in the coefficient matrix, and we will be replacing it with the b vector, and will be determining the determinant of that and dividing the determinant of the determinant matrix, the coefficient matrix we have determined before. So for each of the variables we can easily evaluate or calculate using this technique. That is the Cramer's rule. That is very well known rule for you, so I will not be giving much emphasis on that. I will be just simply solving a math problem regarding that, so that it will be easier for you to understand. So let's move to the question for solving that. So now we'll be learning how to use Cramer's rule. The question will be like, use Cramer's rule to solve. Okay, in the exam, what is the fact? If I give you a set of equations and I say or ask you to solve this without mentioning any rule, then you can use any techniques. And if I ask you to solve this according to a particular rule or technique, then you must follow that. Okay. The question say 0.3x1 plus 0.52x2 plus x3 is equals to minus 0.01. This is the first equation. The second equation I'm writing here, 0.5x1 plus x2 plus 1.9x3 is equals to 0.67. And number 3 equation is 0.1x1 plus 0.3x2 plus 0.5x3 equals to minus 0.44. Now we need to solve this. So now we need to solve this thing using Cramer's rule. So let's not waste time and move forward. The solution. The solution will be starting from here. First of all, the determinant. You know, the coefficient matrix. I don't want to write the coefficient matrix or the matrix in separated form now. Rather, I directly determine the determinant of the coefficient matrix. The determinant of the coefficient matrix will be like this: 0.3, 0.52, 1, 0.5, 1, 1.9, 0.1, 0.3, 0.5. And the determinant of this, how to calculate the determinant of this: 0.3 multiplied by 1 multiplied by 0.5 minus 0.3 multiplied by 1.9 minus 0.52 0.5 multiplied by 0.5 minus 0.1 multiplied by 1.9, and finally plus 1 0.5 multiplied by 0.3 minus 0.1 multiplied by 1. And what the calculation says that the value will be minus 0.0022, if I'm not wrong. This is the determinant. Now how to get the value of x1? x1 will be getting the value of x1. The determinant will be here, and the determinant of another matrix which will be replacing the values of this one coefficient of x1 with this vector, this one. So it will be minus 0.01, then 0.67, then minus 0.44, replacing here, and the other values of the coefficient matrix will remain the same, 1.9, 0.5, and this will be equals to 0.03278, 0.0022, and which is equals to minus 14.9, we can say. So how to calculate the value of x2? In the similar way we can calculate this. We'll be only replacing the value coefficients of x2, and all other values will be same. This will be replacing with the value of constants, 1, 1.9, and 0.5. Now we need to solve this determinant. You can solve this determinant using calculator as well. If you don't know how to use the calculator, please learn this thing. This will give you a soft hand in the exam as well. In this particular course, there is no alternative to using calculators in a swift manner, and otherwise you will not be able to complete all the question answer in the exam. So this will be x2 and x3, where we'll be replacing the coefficients of x3 with this constant values. All other things will be similar to the coefficient matrix, and this will be giving you a value like this one. From there, the value of x3 is 19.8. So our answer as a whole, we can write x1, x2, and x3 will be equals to minus 14.9, minus 29.5, and 19.8. And this is the solution for this particular problem of Cramer's rule. Now, what is the problem with the Cramer's rule? The first problem is that whenever you will be using it for more than 3 numbers, even 3 numbers will make it difficult for you in some cases when you will be trying to solve this, just because the determination is not an easy thing for you. Only the calculator can give you the determinant of 3 by 3 matrix as it is shown there directly. Unless you use calculator, it will be difficult for you to solve this, and that's why even 3 by 3 matrix is a very tough task for you. So if I give 4 number of variables, that will be really difficult for you to solve, even if you are using calculator. So that's why as much as will be increasing number of variables, there will be a huge determinant you will have to solve every time. Say the determinant for 4 by 4 matrix will be a large one. 4 by 4 matrix you will have to solve first using your hand calculation. Then 4 variables, x1, x2, x3, x4, for each of these variables you will have to again solve. For each of these variables you will have to solve a new 4 by 4 matrix. So for 4 you will have to again solve 4 extra determinants using your hand calculation, so it will be very much tough task for you to solve. So that's why we'll be trying to get a value. And in real life problem where there are multiple number of variables are there, not only 4, say 5, 6, 7, or maybe more than that, and hopefully while solving the truss, say I give you a truss. This is a practical example where you need multiple number of equations to solve. Say this is a truss, and as this is a truss, the number of unknowns is not very less. There will be 2 reactions, 2 unknowns, there will be another unknowns, 1 unknown, 2 unknown, 3 unknowns, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 18 unknowns are there. If I ask you to solve all these unknowns, what will happen? Say there are loads given there, 5k, 2k, okay, 9k. So loads are given here like this. So, but you need to solve this. How will be solving this? 18 unknowns. And can we solve this? That is another question in your maybe in the 3rd year or in the 4th year. You'll be learning how whether we can solve this truss or not, whether we can say this is determinant or not. That things we'll be learning there, but that is not our concern here. But what I'm trying to make you understand this, from the static equilibrium equation you'll be getting three equations. So 3 equations. So for solving 18 unknowns we need 18 equations. So whether we'll be getting 18 equations or not, that is our main concern here. So we'll be getting 3 equations from the equation of static equilibrium. That is one thing. And from each of the joints, as you can see here, you'll be getting the one, that is 1. This is 1 joint, 2 joint, 3 joint, 4 joint, 5 joint, 6 joint, 7 joint, 8 joint, and there is 9 joints, as you can see from here. So 9 joints are there. From these joints you can also calculate from each joint. From each joint there are 2 possible equations, summation of fx0, summation of fy0 individually. So from each of these equations, each of these joints, you will be getting 2 additional the additional equations. So 2 multiplied by the number of joints you will be getting as equations. So obviously that will be covering up your solution for this particular truss, and that will make you easier for solving the truss. So there are how many numbers of joints? I have said 1, 2, 3, 4, 5, 6, 7, 8, 9. So now 9 number of joints will give you how many? 18 number of equations as well. So 18 equations plus 3 equations, there will be 21 equations. But there are something that some joints will be giving you the same thing, which will be getting using the overall static equilibrium equations. So some things will be cancelled out. It will become, finally the summation will not be 21 and that will become 18. That is not our concern how to discuss this. That will be the task of in the 3rd year course structure we will be learning. But the thing is that whether we are getting 18 equations or not, and if all these are consistent, then we'll be getting the 18 equations, and whatever the 18 equations are, that doesn't matter. Even if you get more than 18 equations, if all those are consistent, that doesn't matter. You can use either of the 18 equations from the 21 if you get to solve this total truss. So all the unknown, all these member forces you'll be getting, so while solving this 18 number of unknowns and 18 number of equations. So how to get this 18 number of equation? Can you solve this using Cramer's rule? Will that be a task of the what we say intellectual to solve this using Cramer's rule? No, not like that. So that's why we need a technique. The technique the computer will be solving, and the technique which is a repetitive task, as the computer, we know that the computer can solve anything or do the repetitive task very well, and it just because the IQ of computer is 0, whatever we will be asking him, it will be doing accordingly. So that's why a technique we should be developing, so that the repetitively the task will be done by the computer to reach to that solution, so that we don't have to waste time as well as the answer script to get the solution. So that is the technique. That's why we are moving towards a new technique, and that technique is called the Gauss elimination technique, and we are moving to that particular solution. The Gauss elimination. Here the two main principles are the forward elimination and the back substitution. Using these two techniques, these two principles, we will be performing a Gauss elimination to solve a system of linear equation. As you can see, what is forward elimination? Forward elimination is to create an upper triangular system, so that if there are n number of equations and n number of unknown, in the first equation all unknowns and all coefficients should be present. In the second equation, first coefficient along with the first variable will be vanished. Only n minus 1 number of variables will be present in this equation. In the third equation, the first two variables will be cancelled out, and from 3 to n minus 2 numbers of variables will be present. And as we move further, we'll be getting an upper triangular matrix where in the left portion all the variables will be 0 and all the variables or coefficients will be present, non-zero coefficients will be present in upper triangular system, and those will be equals to b1 b2. In the last equation, what will happen? All the coefficients except xn of the xn will be 0, and this new ann multiplied by xn will be equals to a new bn, and from that we'll be getting this upper triangular system will be getting the original solution using the back substitution, as you can see. So from back substitution, from the lowest, the final equation, we will be getting easily xn equals to something, as all other coefficients are 0. And from there we'll be getting it again into the next, the previous equation. So that's why we are calling it back substitution, that as you know now xn, in the previous equation there are two coefficients of xn minus 1 and xn. Two coefficients are there of xn minus 1 and xn accordingly equals to something as a constant value. And as you know xn from the this equation, so you can put the value of xn in this equation. Just prior to this one, the xn value is known, only the xn minus 1 will be unknown, and from that particular equation you can easily determine the value of xn minus 1. And that's how we will be proceeding, and back substitution will be done unless we get to this first equation where all the coefficients, all the variables are known from x2 to xn except x1, and these final equations, while putting all the values, we will be getting the value of x1 accordingly. And this is the technique of Gaussian elimination. This main technique is dedicated for a computer, so that the computer can perform this task repetitively. Just just going for forward elimination and then going for back substitution rather than going for Cramer's rule, which is very tough task for not only us but also for the computer as well. So if I ask you how to conduct the forward elimination, that is our next question. But before that, you will have to understand that we need to create something, an upper triangular matrix like that, as I have said, and then we will be going for the best back substitution. Now come to the point how we will be conducting the forward elimination and how we will be going for the back substitution. That is our next question. And if I give you a question and ask you write something about forward elimination, then you will have to interpret this thing accordingly. And also if I say you to write down something about back substitution, you will be giving some examples and explaining this thing in your answers app as well. But the main thing, the technique I have clarified you, the first thing. Now come to the point how we will be going for the forward elimination. To make the forward elimination, what we will have to do? Then if I want to, first thing is we'll have to eliminate the coefficients of x1 from all the equations except the first equation. So a21 will be eliminated, a31 will be eliminated, a41 will be eliminated, accordingly an1 will be eliminated from here. That is the main concern. So how to do that? To make a210, we better multiply a1a equations with a21 divided by a11, which will give you a21, and all the things will be changed similarly. But after that we will be subtracting develop the modified equation of a1 from this a1b, so that a21 and a21 will be cancelled out, and the first coefficient of this first variable x1 will be cancelled out from there. Only the remaining coefficients will be all the coefficients of from x2 to xn. That is our forward elimination technique. And the similar thing, I will be multiplying a1 with a31 by a11 and subtracting this from 1c, which is not shown there, to eliminate a31 from this particular equation. So first step will be cancelling out all the coefficients of x1, and in the next step the same thing will be done with respect to this a22. This a22 will be there, and all a32, new form of a32, new form of a42, all this up to the new form of an2 will be cancelled out. Why I'm saying that new form? Just because whenever you'll be subtracting this thing from the equation 2, this will be subtracted, but a22 will not be in its original form. This will be changed to a new form. A22 means it will become a22 prime, a new value, and a32, this will be again changing into a new form. So then the changed value will be considered for forward elimination in the next step. So it will be clarified to you if I go further and give you an example that will be clear to you, I think. So I will be going for example. So see there a21, the second equation, that is 1b, that is 121x1 and plus a21 by a11 a12 x2, it will become like this, just because if we multiply it, 1a with 121 by a21 by a11, this one will become a21, and this one will become as it is shown here, a21 by a11 multiplied by a12 into x2, and like all these things will be multiplied by the same thing, and finally you will obtain this equation, the new equation. However, this one now, this will be subtracted from 1b. So 1b, as you know that 1b is 1 2 1 x1. So x1 coefficient of this equation has changed to 1 2 1 as well. This is 1b modified 1a, sorry, this is modified 1a, and this is 1b. So if I multiply 1b, if I subtract this modified 1a, this one, with modify the previous 1b 121, sorry, a21, then it will become like this. The first term will be vanished. The second term was a22 will be subtracting this one, this term a21 by a11 multiplied by a12 into x2. This one, the coefficient of x2 will be like this, and all these things will be changed in similar manner, as you can see. For our convenience, we can say that this the coefficient of x2 has been upgraded to a22 to a prime 22. That means one time this has been changed, and all these things prime indicates that this has been changed one time. So this procedure and then repeated for the remaining equations. So 1b, not only the 1b will be changed like this, the coefficient of x1 will be vanished from all other equations, from 1c to this is 1c, all other equations in between this and up to 1c. So this will become like, so for the next equation, it will be multiplied like 1a will be multiplied by 131 by a11, and the modified equation of 1a then will be subtracted from the next equation, where the coefficient of x1 is a31. So therefore the coefficient of x1 will be vanished from that equation as well. So this will be repeated until the coefficient of x1 of for equation equation 1c, where this one will be vanished as well, and this will become a prime and 2x2. Prime means this has been changed one time. So this will become like this, as you can see here. So all the coefficients of x1 of the equations except the 1a has been vanished and cancelled out. So only remaining is this, all the coefficients of from x2 to xn for all other equations, as you can see here. And 1a prime 1 prime means indicates that this has been changed one time. So now what is our task? Now just forget about the 1a. Now just consider the focus on these equations. Now the role of this second equation will be like the first equation in the previous state. So now we'll have to cancel or vanish all the coefficients from a32 prime to an2 prime. That is the coefficients of x2 will have to cancel out from this, and after that we'll be going for only the remaining will be the coefficients of x3 to xn for all the equation except this second equations, and the reference will be this equation. So we will be now referring to this second equation, and we'll be applying the modified subtraction to all other equations there individually. So now for the next step, what will happen? For changing this equation, we'll have to multiply this second equation with a prime 32, a prime divided by a prime 22. Then the result will be, this will become a prime 32, and then if I subtract this from this equation, the first term, this one, the coefficient of x2 will be cancelled out easily. The similar thing I will be multiplying by with a prime 42 divided by a prime 22 for, and then subtract it from this equation, which you cannot see here. Then the coefficient of x2 for this equation will also vanish here. So the next thing it will become, what will become, referring to this equation, if we change this thing, this will be vanished, and this will become a33 double prime, just because this will be changed as well. The influence of the subtraction which applied here, which made this vanished, and it will be changed as well. So we'll denote this as a double prime 33 x3 afterwards. Okay, so the thing, if we proceed similarly, the remaining thing, the third step, this will become that double prime 33 x3. Now all this will be double primed, just because this has been modified 2 times, and these things will be continued until we get to this thing, that the last equation will only keep the xn coefficient, and all other coefficients will be cancelled out. And also these things as well, you must focus on these things as well. These constants are also changed similarly as the equation has been applied. The subtraction is not only done in the one side but also the both sides. So finally this procedure, this step will end up in this position. As you can see here, this thing, instead of showing prime, I have written there n-1. This is not the power, rather this is the number of prime. This is the number of change which has been made here over this. So the resultant result is the xn's coefficients which has been multiplied n-1 times and become a n-1 prime time prime and nn. So this is the coefficient final, and this is the constant term. And now the back substitution will have to be done, and this back substitution will be starting from the very last equations, where we can easily understand, and the determination of xn can be done. As you can see from there, xn can be easily calculated according to this formula. And the similar thing for all other equations we have derived. Don't be afraid of this thing, don't be frightened, just because this is nothing but the general equations which will have to be applied for all the equations in back substitution. So if I ask you to write down the back substitution procedure, you can explain this thing, and this is the general term. So whenever we'll be getting xn values, then we'll be applying these things for the next equation, the previous equation, where we'll have xn-1 and xn, two variables there and a constant value. But if we know once the xn value, then we can apply this in the previous equation, and you will be getting this the value of xn-1 from that equation. And if the back substitution goes on, then for each of the term xi, if I ask this is xi, so you will be understanding all the values except xi, that is from j equals to I plus 1 up to n. You know all the values, that is, if I want say for example for this value, I know all the other coefficients of all other all the other variables except this one, so only the remaining is this coefficient. So we can easily determine this value using this equation. So this is just general terminology for computer users. You don't have to remember or memorize this thing. This is nothing important which you'll have to mention in your exam as well. It's not necessary. The explanation is the main thing which you will have to do in the exam. However, the Gauss elimination, if I say if I make overview of this at a glance, you can see there a11, this second equation will be changed one time, so this will become a prime 22, a prime 23, and b prime 2, and finally this will be changed two times, so this will become a double prime 33 equals to b double prime 3. So this is the forward elevation what we have talked about. So forward elimination is all about making the upper triangular matrix. As you can see, all other values coefficients are 0 in the lower side, and upper triangular matrix is the only matrix where all the values are non-zero. As you can see here, forward elimination. This is forward elimination. If you are asked to explain this thing, you can just easily depict this thing in your exam script, and that will be enough, I think. However, the back substitution, as you can see, once you get the upper triangular matrix, so using upper triangular matrix, you can obtain all the values accordingly, and starting from the very last equations to the first equation, you can proceed accordingly as it is shown in there. So now we'll be watching an example problem of Gauss elimination technique, where this Gauss elimination technique has been applied to solve a system of linear equation. For our convenience, we are taking obviously we are taking three values, three variables for our convenience, but it can be applied to any number of equations. And the repetitive task which we have established or developed in this case, that will be teaching this thing to the computer, which will be performing the task accordingly to give us the exact solution of the system of linear equation, as you know. So now the question for you is to solve, use Gauss elimination Gauss elimination to solve. One thing is I can just skip these things and I can skip explaining all these things from explaining or interpreting to you, but why I'm giving focus in these things and I'm taking time. I hope you wouldn't mind that within this Ramadan period as well I'm taking so lengthy classes, just because to make you understand about this. If I just keep you free of these things and just not giving overview, just giving the results and the procedures, I'm just showing these things to you, then you will make it very much uncomfortable. I think that's why I'm just explaining all these things. I hope you wouldn't mind. So use Gauss elimination to solve 3x1 minus 0.1 x2 minus 0.2 x3 equals to 7.85. Then 0.1 x1 plus 7x2 minus 0.3 x3 is equals to minus 19.3. And the third equation is 0.3 x1 minus 0.2 x2 plus 10 x3 is equals to 71.4. So these three equations are given there. This is a system of linear equation. Using this thing, apply the Gauss elimination technique to solve this one. So how we'll be proceeding there? First of all, just give the equation number as this is equation number 1. This is equation number, we say 1a. This is 2a, and this is 3a. This will be changed multiple times. That's why I have given a after this. Okay. However, let's proceed. Now, what we'll have to do, you know that the first task is to eliminate all the coefficient of x1 from the equations except 1a. So we'll be keeping the coefficient of x1 in this equation, but eliminating the from this equation 2 and 3. So for that, what we'll have to do, first we'll be referring to this 1a to equalize this coefficient. What we'll have to do, we'll have to multiply 0.1. So we'll have to multiply 0.1 by 3 into 1a, as you can see here, and subtract it from the equation 2a. So 2a minus this will be giving us the new equation, where this one will be cancelled out and the remaining will be this one. So it will become 7 minus 0.1 by 3 multiplied by this 0.1. So this minus 0.1 will be multiplied here, and this is the coefficient will be of x2, and for x3 it will become minus 0.3 minus this 0.1 by 3 is multiplied with the coefficient of 1a, that is 0.2. As you can see here, this is x3 which will be equals to 7.85. The application of this one will be in this part as well. So there will be minus 19.3 minus 0.1 by 3 multiplied by 7.85. This one. Okay. So it will become, the modified equation will become like this: 7.00333. You can write x2 minus 0.29333 x3 equals to minus 19.5617. So you can see here that this the equation 2a has been changed, and this is changed. So this is, if it were a22, now the modified the coefficient of it has become a22 prime. That's why we have used prime here. All these things, all the coefficient has been changed, that's why we say this, the new equation, that is 2b. And the same thing we'll have to apply over and the equation 3. So for changing and vanishing the coefficient of x1 in the equation 3a, so what we'll have to do, we'll have to multiply it with 0.3 by 3. 0.3 by 3 will be multiplied to equation 1a, and it will be subtracted from the equation 3a. So let's write down this thing. This will be the 3a minus 0.3 by 3. Equation 3a will be we will subtract the 0.3 by 3 multiplied by 1a from this equation, and it will give you what? I'm just writing as a whole. This will be cancelled out, this 2 will be modified as well as this one, so it will become, so you will do these things in of your own to verify that I have made the correct calculation or not. If the calculations are something wrong you have found, if you found, then you will correct it of your own. I'm just writing it as I have calculated 10.02 x3 equals to 70.615, and this equation, new equation, will be named after 3b, the new developed equation. So now we have the system of we have this equation. I will be importing this thing again. 1a, this, sorry, I'll be importing this thing. I've imported this thing, as you can see. Not only this one, I will be also importing all other things like this one. See this equation 2b, this 2b will be also imported here. We have imported this, and also equation 3 as well. This one has been imported accordingly. So x2 this is 3b, x2 here, forget about this. So now you see x1, x2, x3. So x1 has been cancelled out for both of these two equations, and this has been modified as 2b and 3b. Now the next step, what we'll have to do, to eliminate the coefficient of x2 from 3b, and if there are other equation as well, like 4b, 4c, 4d, we'll have to apply the same thing for all those equations as well, to cancel out all the coefficient of x2 from those equations. But as there is only 3 variables and this is the only equation remaining, so we'll be only cancelling out the vanishing this coefficient from this equation. And for that, what we'll have to do, we will be multiplying the 2b with minus 0.19 divided by 7.00333, and it will be multiplied to 2b, and which will be subtracted from 3b to get the new equation. It will give us the x2 coefficient will be cancelled out, and we'll be getting, and this is a very small amount, as you know. although this one will be cancelled out and very few thing will be subtracted from this one, just because this is a very small terminology, as you know, so it will remain almost the similar thing, that is 10.012 x3 after subtracting this thing from this 3b, and this will be equals to 70.0843, and this is our equation 3c, new modified equation. And now the back substitution starts from 3c. From 3c easily we can calculate x3 as 70.0843 divided by 10.012, and this will be equals to nothing but almost equals to 7. So 7 we can say this is the value of x3 we have calculated. Now from 3b we'll be calculating the value of x2, as we know the value of x3 in this case, so only the remaining is x2. So 0.19 x2 is remaining here. So sorry, 2b, I forgot to write it. This will not be 3b, rather it will be 2b. We are using here twice b, and from 2b we'll be writing, although we can use 3b, but remember one thing, this is the procedure which you must maintain. You can also use as I have shown there, 3b you can also use for calculating the value of x2. It's true that you can use 3b. There's a good thing which has arisen here. I must explain this thing. You can also use this 3b to calculate x2, but the procedure doesn't say so. The Gauss elimination technique, what is the technique that you must follow? You cannot go beyond that. So that's why you must follow this particular thing. So we'll be using this over twice b. So the final upper triangular matrix which we have formed, this will be replaced by this one 3c. So whatever x3 we have got, we will be applying this to 2b, this one. So, and whatever we will be getting x2 and x1, we will be applying it over this 1a equation, 1a. So whatever, we'll be taking this thing anyway. So 7.00, so it will not be like this, rather we'll be taking 7.00333 x2 minus 0.29333 multiplied by the 7 which we have got in the last equation, and which is equals to nothing but minus 19.5617, minus 19.5617. So from this equation x2 can be easily calculated, and x2 will be in this case minus 2.5, and the similar thing we'll have to apply over equation 1a, which is this one. So 3x1 minus 0.1 multiplied by this minus 2.5, and 0.2 minus 0.2 multiplied by the x value is 7, which is equals to 7.85, and from this equation x1 can be easily calculated, as you can see here. The computer program which we have written, we have used as iteration, as you have seen while describing the back substitution, is nothing but this thing. So whatever it is, this value will be equals to this constant value minus all the terms, all these terms, this term or this one minus all this term will be sent to this side, and the division will be made by the coefficient of this one, of that equation. So this is the general term. What we have written there, this one, this is, say for example, this was b1 minus sum of all these things, that is from all the coefficients, that is a, I, x, I, and this was the power. This may be the power, that is the prime thing. This is the prime. So according to which we have modified. If this is 1a, no modification has been done of the over the coefficient. It is twice b, so 1 modified, so 1 prime will be there for all the coefficients. If this is 3b, 2 prime will be there for all the coefficients, and divided by, it was divided by the coefficient of this one, that is the x1. So that was the general iterative term we have used for explaining the Vex substitution there. So no need to memorize this thing. I am again telling you that you will have to understand the thing, not necessarily you'll have to memorize this. Okay. Anyway, so this is the solution. So using this Gauss technique, you can easily solve the system of linear equation now, I hope. So therefore, we'll be finishing it off. Although there are different techniques remaining as well, but in our course or in undergrad program, our syllabus doesn't match with all those techniques to include in this syllabus, just because if we just focus on one topic, we cannot touch all the topics there. The main task of this course is to make you introduced with all the topics, all the basic things, so that you can proceed further accurately. So that's why we are just giving a smooth touch on all the topics here. So the limitations of Gauss elimination now we'll be discussing about. The Gauss elimination technique, if you can see here, that what is the limitation here? The first limitation, as if I say that the main limitation will be like if in any case you see a11, this a11, all the things are done and started according to this thing, you know. So think about this. If a11 becomes 0, it is possible that the coefficient of any variable is 0. So if any case the first equation, the first variable's first coefficient becomes 0, what will happen? You cannot go further, you cannot move one step after this. The Gauss elimination will be totally collapsed. This particular thing will be collapsed, just because you cannot use this one, the a11. So what we have done, the first task was to multiply a21 divided by a11 with this one. So if we use a21 divided by a11, this a11, if it is equals to 0, then this total thing will be it will be undefined. So you cannot go further using this technique if just a11 becomes 0. And not only a11 if it becomes 0, but also for all other terms after application of after application of this technique, if any either terms, this first term of the upper triangular matrix for each of the rows, if it becomes 0, then the next move will become obsolete or invalid for you to go further. So this is the main limitation for Gauss elimination, which we haven't explained. So for solving these problems or complexities arised for these problems, we have to modify the Gauss elimination technique, where the first thing, it might be like all the coefficients should be non-zero. This is the first thing. Or the another thing which we can do, that we can rearrange the equations in such a way that the coefficients of the first element of the upper triangular matrix of the all rows will never become 0. That is the technique of modification, or there might be different techniques as well, which the Gauss elimination how we can modify and go further for our calculation, so that no problem will be will give a rise from this particular problem. So that's why what we have discussed in the first case, that there are different techniques available. Naive Gauss elimination, this one is the naive Gauss elimination. Why I have said this as naive Gauss elimination? Just because this is naive, it cannot go further if just one element of the upper triangular matrix first element of the either row becomes 0, it will become invalid, so you cannot go further with this. That's why this is called naive Gauss elimination, in which you must maintain that all the first coefficient values of the variables in the upper triangular matrix must be not equals to 0. It must give you non-zero coefficient values for the equations. Only then the Gauss elimination, this particular one, the naive one, will be valid. Unless it is 0, it will be valid. But if it becomes 0, it will become invalid. That's why the modification techniques are there. That is the Gauss-Jordan, Gauss-Seidel. Those are the upgradation of this technique, where the complexities arise due to naive Gauss elimination have been given effort to modify. So those we can also apply. So if once you know the naive Gauss elimination, the modified technique, you'll find it easier to understand, I hope. So that's why we are not we haven't included those techniques here. We are just introducing the naive Gauss elimination before you, and make you to think about the computer techniques, how the computer works, and how we can give the task to the computer, so that repetitively these things the computer will be doing. What it will be doing? It will be multiplying something, that's the value which will make the first coefficient of the all other equations to 0. That is the task of the computer, repetitive task, the forward elimination to create an upper triangular matrix. This is the first task. The next task will be the back substitution, according to which it will be proceeding further to give you the solution of all the unknown values of the system of linear equations. So this is the system of linear equation, if in short what we have discussed today. So we'll be going to another topic to finish before we finish today, and the topic is the eigenvectors and eigenvalues. This is very renowned terms we use in different techniques. Even it is applied in the chemistry, the inorganic chemistry. We also use this in the physics. We also use this in the quantum mechanics. So in different sectors we use these eigenvalues, eigenvectors. Also in civil engineering, maybe you will be learning this in your higher level studies, say for example postgraduate or in the PhD topics, where you'll be facing some problems where the equations will giving you eigenvectors or eigenvalues. You'll find it. So this is possible. So in structural dynamics it is possible, while analyzing structure, stress, strain analysis in details, you will be finding these things, hopefully. So that's why eigenvalues and eigenvectors is very important, and we'll be learning here what is eigenvalues and what are the eigenvalues and eigenvectors accordingly. So first, before we go to this one, I will try to make you understand about one thing, that is the concept of non-trivial solution. So far we have talked about the system of linear equation, as you know. Look, I'm giving example in front of you. It will make you understand about this thing. That is, let's say about two equations I'm giving you example about. This is the example here. 5x1 plus 7x2 equals to 0. This is equation number 1. And the another equation I'm giving you, 15x1 plus 21x2 equals to 0. This is the equation number 2. These two equations, if I ask you to solve this thing using a calculator, if you use the calculator to solve this, you will be getting math error. Directly you will be getting math error. Can you say what is the reason behind this, why we are getting math error while solving this thing in equation mode of the calculator? Well, basically the thing is that these two equations are identical, the same thing, as you can see from here. Although we have used two different equations to denote these things, these are basically the same thing. I have just multiplied 3 with this first equation to get the second one. And if I write it down in matrix format, I can write it like this: x1, x2 which is equals to 0 0, and we can write 0 as well, like this. So this is the matrix form of this particular equation. Why we have, just because we have said that we have multiplied it with 3, the same equation we have used 2 times, so that's why it cannot give you a particular definite solution. That's why it is showing you math errors. As basically this is only the one equation of x1 and x2, and to solve to get a particular set of solution for x1 and x2, we must need 2 different equations, as you know. And as we are getting just one equation, so there are multiple combinations are possible for x1 and x2, as you know. So there might be, for example, it might be the x1 value might be -1/5, and x2 value may be 1/7, then it will become 0. Or the x1 value might be 1/5, and this might be 1/7, it will be equals to 0. And also if x1 equals to 0 and x2 equals to 0, it will also become 0. However, so this is the possible sets are multiple or infinite sets of solutions can be obtained from these 2 equations. That's why it will be giving matter in the calculator. But what will happen for this particular set of equations? If I give you the example of 5x1 plus 7x2 equals to 0, and 9x1, this time I am not equalizing this thing, x2 equals to 0. So these 2 equations are there, so you'll have to use the calculator. This time you will not be getting math error, I bet. Just because of what? Calculator, use this thing, you'll be getting the value of x1 equals to 0, x2 equals to 0. But because of what? The first thing is all the right side components, as you can see, the constant values are 0. This is the first focusing point. The second one is that there is no other combination of x1 and x2 which will give you the 0 value for these 2 equations, just because different combination 9, 21, 5, 7 are used in both cases, but both values are giving 0. It is only possible when the value of x1 and x2 are 0. In this case, this is the only solution. Then we say this is the trivial solution. Trivial solution, that means the variables will be 0 to make the equation 0 in the right side. All the values are 0 in the right side just because of all the variable values are 0. In this case, we say this is a trivial solution, as you can see here. But in this case, as I've said, non-zero values can be the solutions of x1 and x2, although there are multiple number of solutions available. But as there are non-zero solutions are available, so that's why we say this as non-trivial solution. Non-trivial solution means the solution of the equations where the values of variables will be non-zero. Non-zero means not necessary that all the values x1, x2, all the values should be non-zero, but rather than that, x2 may be 0, but x1 will not. That means at least one variable must be non-zero. In that case, we will be saying that this is a non-trivial solution. So I hope you have understood this thing. Non-trivial solution will be there when the values of x1, x2 and x3, all the variables, at least one variable is non-zero, then we'll be calling this as a non-trivial solution. And in the cases where x1, x2 or all the variables must have to be 0 to satisfy the equations conditions, then we'll be saying that as a trivial solution. So what is the purpose of this trivial solution or non-trivial solution? I will be giving you the interpretation here. We are using these things in different purposes, different applications. So I will be giving you the very simplest example which we face in the intermediate level. You must have faced this thing, I hope. So I will be introducing that thing in front of you to make you understand why this is important. So first thing, you will have to focus that all the constant terms in the right side, it will be 0, and the matrix form, this should be where this should be in such a way that a non-trivial solution will be satisfying this thing. So how to determine that? The thing I have said that I have multiplied 3 with this one, so basically this is the same equation. This is not the formal technique to say. The formal technique will be to determine the determinant of this particular matrix. So if I say the determinant of this one is equals to 0, so whenever the determinant of the matrix, coefficient matrix, will be 0, then we can say that the non-trivial solution exists. And whenever you come to the point that the determinant of this matrix, if I write down like this, 921, this will be non-zero for sure, I bet. So if you find that this one is not equals to 0, then you will be able to say that the trivial solution will exist. Trivial solution means in the cases where you will be getting that the values in the right portion is 0. First of all, this is the first thing. Then if the determinant is not equals to 0, then you can say this is the trivial solution there will be existing, that is all of the variable values will be equals to 0. And if the determinant is equals to 0, the determinant equals to 0, then you can say that non-trivial solution also exists. Okay, so I'll be giving you the interpretation where we are using this thing, eigenvalues and eigenvectors. Eigenvalues, the word eigenvalue comes from the German word Eigenwert, where eigen means characteristic and word means the value. So eigenvalue means characteristic value. Why do you need to learn about the eigenvalue? I will be giving the example. Before that, I am just establishing the fact using the equation I have just given you the example of. Say, for example, if I say that two sets of two equations are like lambda plus 3 minus 0.75 minus 1.5 minus lambda plus 0.75, this is a matrix, and this one a1 a2 equals to 0 0. So this is a case where all the right side, the constant values are equals to 0 in these two equations, and also there are two variables a1 and a2, and this is the matrix. So now if you know that, first of all, 0 0, first thing is possible that a1 and a2 0. You can say without any hesitation, if a1 and a2 become 0, whatever the matrix is, it doesn't matter, it will obviously always become 0 all the time. So it will become trivial solution. But if you know that this a1 and a2 are non-zero values, this is known that you don't know the exact value of a1 and a2, but you know that a1 and a2 cannot be 0. So that means non-trivial solution is existing there. Non-trivial solution exists in this case. So that means a1 and a2 will not be equals to 0. At least one will not be equals to 0. So in that case, what will happen? The first thing that in this case we will have to say that as a1 and a2 cannot be equals to 0, so it must be non-trivial solution, and in that case determinant of this particular matrix lambda plus 3 minus 1.15, the lambda is unknown, that's why I am giving this example, minus lambda plus 0.75, determinant of this equals to 0, and from this equation you can determine the value of lambda, from which you can easily determine the values of a1 and a2. So that is the significance of what we say, that is the significance of our eigenvalues and eigenvectors. Now we'll be coming to the point. Eigenvalues, these values of lambda is called the eigenvalue. This value of lambda is called the eigenvalue. The values from lambda, what we'll be getting, we'll be calling that as eigenvalues. And for the values, say there will be two values, say 0.5, 0.6, two values we'll be obtaining from this lambda, these two equations, as we'll be getting a square of lambda in these equations. while determining the determinant. So lambda will give you, say, two values, so two eigenvalues will be there. And if I put the value of 0.5 in there 0.5, then you will be getting a value of a1 and a2, which will give you non-trivial solution, that a1 and a2 will not become 0 in that case. And also, if you use lambda equals to 0.6 in these two cases, then you will be getting a1 and 2 value as non-trivial solution, and obviously there as well you will be getting non-zero values for a1 and 2 as well, so which meets our criteria we have discussed about. So the values are 0.5 and 0.6. We have said these are the eigenvalues, and the vectors which will be obtaining that a1 a2 combination. If we use 0.5 as lambda, then we will be getting a vector of a1 and a2, that means the solution vector, the a1 a2. That vector will be called the corresponding eigenvectors of 0.5. And when we'll be putting the values of 0.6 into the equation, then we'll be getting another vector of a1 and a2 as solutions. Then the vectors of a1 and 2, the corresponding value will be saying that this is the corresponding eigenvectors for the eigenvalue of lambda equals to 0.6. So this is the significance of eigenvalues and eigenvectors. Eigenvectors are used in such cases where the right side of the equations are 0, but we also know that the variables are non-zero. At least one variable will be non-zero in this equation. So therefore, another unknown term that is existing in this equation, which we'll have to determine, that will be the eigenvalues, for which value of that particular unknown will give you non-trivial solution, that is eigenvalue, and the eigenvector is the corresponding value using that unknown value. The corresponding vector will be obtaining, that will be called the eigenvectors. I hope you have understood this thing. Now I'm giving the example where you will be facing this thing. I'm giving you the example here. Eigenvalues, if I give example of this one, the spring problem in physics, if you say the spring constant is k, the mass m1 and m2, which will be pulled here in this direction, so the displacement will be x1 and x2. As you can see, x1 and x2 will be the displacements accordingly, m1 and m2. So in this problem, this is a simple harmonic motion, as you know. So this is written here, the two masses displacements to be denoted by x1 and x2. The spring constant is k. So now if we apply Newton's second law and third law of motion to develop force balance each mass, then we'll be getting what I'm just not writing there, I'm just showing you in the slide. I hope you will be understanding this thing. The first one, the acceleration of m1 will be, as it is displaced with x1, we can say the double derivative of x1, the displacement will be the with respect to the time will be the acceleration. As you can see, m1 into a1, I can say this is a1, m1 a1, this is the force in the first body, will be equals to minus kx1 according to the Hooke's law of motion. As you know, the spring's constant k multiplied by x, and this is negative according to the theorem of simple harmonic motion, if you can remember. And why we have added another term here, just because this m2 is moving forward x2, this is moving forward amount of x2. If this is going x2, there is a portion of m1 within this x2, and that portion is x1. So if we will have to eliminate this x1 from x2 to get the original displacement of m2, that's why we have just focus on this one first, m2 into acceleration of this one. So I can say this as a2 equals to spring constant k, and the displacement, the original displacement of m2 with respect to m1. So if we consider m1 as constant, then we'll have to subtract the x1 value from this x2. However, this is not our derivation or physics class, so you don't have to feel it uncomfortable. Just see at a glance. So this is the displacement, the force of what? This is the force of this second spring, this second mass, as you can see. So why we have imported this as negative? We have subtracted this thing from here as well, just because of what? This force is acting upon this one as well. This m2 is going forward, as we know from the law of motion, that each of the particle will have an opposite reaction of the forces. So if it is going, this force is facing towards this direction, it is obviously giving the same amount of force in this direction as well. So if there were no second body existing there, that will be, we would get this minus kx1 only, as it is shown here as well. But as it is, this force is acting after this one as well, so the opposite reaction will giving a negative, the subtraction value, which will in turn become positive in this case, as you can see here. So this is the first equation, and this will be the second equation. So rewriting the equation according to the HSA concept, as you can see, you can rewrite this thing as like this: m1, m2 values and k values. If all these things are given, then we can say the solution is this one. This is the simple harmonic motions solution for displacement a sine omega t minus phi, phase shift if phi is existing there, and omega is nothing but the frequency of vibration, as you know, and a is the amplitude, that is the amplitude, maximum amplitude, which this mass m1 or m2 can go. While rearranging this thing, the general solution for this is like this one. The acceleration can be rewritten accordingly like this one. So if it is x1, we can use x1, and if it is x2, we can use x2 for this, from which a1 is the amplitude of x1 and the mass m1, and a2 is the amplitude of mass m2, and x2 is the displacement accordingly. So if we use all the substitution these two things into the equation, you will be simply getting these values: amplitude of 1, amplitude of 2. Omega is the vibration, as you have shown that the frequency of vibration was omega. So you can simply getting these two equations from the previous two. And finally, if you rewrite these things like the coefficients of a1, coefficients of a2, you'll be getting like something like this. And this thing, if you write this in the format of matrix form, you can write this like this one, as you can see here: minus omega square plus 3 minus 1.5 minus 0.75 minus omega square plus 0.75. So matrix form, we can write it like this. Remember one thing, there is 0 in the right side, but we also know that a1, a2 amplitude cannot be 0. So this is the case. This is the application where we know that the amplitude or the variable's value will be non-zero. A1, A2 both are non-zero. Amplitude cannot be 0, you know. But there are zeros here in the right side of the equation. So if we say A1 0, A2 0, this equation will be satisfied. But we know that A1 and A2 are not 0. That's why we must say that this is non-trivial solution for sure. And for confirming that this is non-trivial solution, what is the condition? The condition is the coefficient matrix determinant will have to be equals to 0. So this one will have to be equals to 0. And that is our concern, from which we'll be getting the values of minus omega square. And this minus omega square, we use this omega square as lambda, as we have shown in the example, as you can see here. In the this is the same equation which we have used here to make you understand about this. This omega is nothing but the omega, lambda is nothing but the omega square. For making you understand about this, we have used lambda, and this lambda is corresponding the eigenvalues, as you can see. So whatever this omega, so we can rewrite this thing, minus omega can be taken out from this equation in a separated form. This minus omega square, a1 a2 equals to 0. We can write this thing accordingly, and this omega square, the value of this omega square will be giving you the result of eigenvalues. So if we assume omega square equals to lambda, and the equation will be becoming like this, and the above equation lambda is called the eigenvalues. As I have said, x is the eigenvector of corresponding to lambda. That is, whenever you will be using one value of lambda in the equation, then we will be getting the set of x, x1, x2, all the variables, or if I say a matrix instead of x, it will be also valid. So whatever the vector, the x vector or a vector, that will be called the eigenvector corresponding to lambda. I hope you have understood. Okay, this is all the similar thing I have said. One thing we can introduce from here, you can see identity matrix we can introduce. For giving the example of this one, I can expand the concept of this. So you can write this as like this one, minus 0.75, minus 1.5, and 0.75 again. This is one thing multiplied by a1, a2, and lambda minus lambda will be out of this. Again I can write as this one as 0, 0. So this thing I can introduce an identity matrix here for this one. This will give you no change in there, you know. Why no change? What is identity matrix? Identity matrix is 1, 0, 0, 1. So if you use this one, that will become lambda multiplied by 1, 0, 0, 1. So it will simply become, you see here, lambda 0, 0, lambda multiplied by a1, a2. So it will be eventually becoming the same thing, lambda a1 equals to, and this will be lambda a2 something, just because in first case you will be getting the a1, a2 will be multiplied by 0, and the second case 0 will be multiplied by a1, this one will be multiplied by a2. So that's why you will be getting this is nothing but the same thing. We can just introduce identity matrix over there, so it will not make any change. As you have seen here, we have introduced an identity matrix here, so it will not give you any problem, create any problem. So now we'll be finishing our today's lecture by conducting 2 math examples. Hopefully you will be able to conduct 2. If we don't get enough time, then we'll be just stick to 1. So let's start with this one. Find the eigenvalues of the corresponding eigenvectors of the following matrix, this one. So let's import this in our script. This is the question. So we'll have to determine the eigenvalues and eigenvectors for this. So how to proceed? First of all, we'll be saying that this is equals to A. This is equals to A matrix. The coefficient matrix, what we say. This A means we have a coefficient matrix of A and multiplied by x minus lambda multiplied by x. X is the variable set, you know, not like amplitude. Now we are just using x. X means x1, x2, x3 will be there as variables, and A is the coefficient matrix, minus lambda is the eigenvalue, and which is equals to 0. Okay. In this case, as it is 2 by 2 matrix, so 2, 0, 2, 0 will be there. If I write it down, it will be 0, 0. Okay. Now the first thing we'll have to do, I will be writing it like A minus lambda into I, that will be equals to this thing, 3 minus lambda minus 0.75 minus 1.5 0.75 minus lambda. So this is our case. So now if we want to make sure that the eigenvalues means what, if we use these equations, x1 x2 might be there and it will be 0 0, but the values of x1 and x2 will be non-zero, or at least one will be non-zero. That will give you the non-trivial solution, and for that non-trivial solution, for which we'll be getting this non-trivial solution, the values of lambda, that will be our eigenvalues. So if you are asked to determine eigenvalues, so now we'll have to use the determinant. So for getting the non-trivial solution, determinant of this must be equals to 0. So determinant of 3 minus lambda minus 0.75 minus 1.5 0.75 minus lambda, or lambda can be put before that, it doesn't matter, it should be equals to 0. And if it is to be equals to 0, you can write it as 3 minus lambda multiplied by 0.75 minus lambda, then minus 0.75 multiplied by minus 1.5, and which will be equals to 0. And therefore you will be getting an equation like this one, 1.125 equals to 0, and from which you will be getting the value of lambda. Two values of lambda will be obtained, 421 and 0.3288, and that will be the eigenvalues. And corresponding eigenvectors, if I say eigenvectors corresponding to lambda equals to, first we will be using 421, this one corresponding to this value, the eigenvectors will be obtaining, that will be getting non-trivial solution for that. So in this equation we'll be putting the value of lambda equals to 3.421. So in this case we'll be putting the value 3 minus we'll be putting the value 3.421, and this is 1.5, this will be same 1.75, this will be 0.75 minus 3.421, and this will be multiplied with x1 and x2. This is the vector which will be getting as the eigenvector equals to 0 0. So if we get the modified value, you will see that this will become 0.421 minus 0.75 minus 1.5 minus 2.671 multiplied by x1 x2 equals to 0 0. From that you can easily calculate the values of x1 and x2, and this x1 and x2 you will be getting. How to get this thing? First thing, that this vector, to represent this thing, there might be multiple number of solution again possible in case of eigenvectors. In this case, what we assume that, say for example, we will be assuming a value multiplier x1 will be equals to s. For example, we will be assuming x1 equals to x. So if x1 equals to x, it will become 0.421 it will become minus 3.421. So minus 0.421 multiplied by s minus 1.5 into x2 is equals to 0. So from this you can get the value of x2 as 0.2807 s. So this s is a multiplier, nothing else. So the eigenvectors we can write the eigenvectors corresponding to 3.421 is, we say lambda 1, we have used 3.421, so corresponding x1 x2 we can write as, this is x means x1 x2, that means x1, if x1 is 0, then x2 equals to 2807s. Now you can ask, okay sir, why we have assumed this as s? We could also assume x2 as s. Yes, you can use you can also assume this as s. It doesn't matter. If you use this one as s, the result will be similar. The s is nothing but a scalar multiplier. So if you use this one, the ratio will be always the same, just because this is not a single solution, but it is a set of solution for which a common solution which has been depicted here. So for different values of s, all the solution you will be getting. So if you have used x2 equals to s, if you have assumed this, it will not make any variation. Rather, the answer will be similar. It's up to you which you will be assuming as s, one multiplier. However, from here we can take the value of s as common, so we can write it like this. And what we do in case of eigenvectors, as this is eigenvector doesn't represent a particular solution, rather it indicates the ratio of the values which we'll be using. So whatever the value is, it will be always maintaining this ratio. If x1 is 1, 1 times, and the x2 will be always this times, whatever the solution is. Keeping eye on that, you can use infinite number of solution which is possible here. But the ratio, this is the ratio which must be maintained. In case of lambda 1, this is the eigenvector, and that's why, as this is the ratio, so most of the times we generally omit this quantity which we have assumed. That's why we will be writing only this one. This will be only enough to depict the result, that is the ratio of x1 and x2 will be like that. Whatever you use, you can convert this to 1 and multiply, and for converting this to 1, you can divide it with minus 0.2807, the first one. So whatever you do, however what you do and how you convert it, it doesn't matter. The ratio must be always the same, and it will be always the same whatever the approach is, it doesn't matter. And the similar thing for lambda 2, if you use lambda 2.3288, it was, for that the corresponding eigenvectors you will be obtaining, that will be 1 by 1.781. So this will be the eigenvector, and as I was speaking, that you can also write this one as a form like, if you multiply, if you make it 1, then it will become, keeping the same ratio, it will become like, if I divide it 0.2807, then 3.5625 it will be minus. So this is same thing. So whatever you use doesn't matter. Also you can use negative in this portion and use this as positive, it doesn't matter. Ratio should be always same. That is our main concept. So this is an example of eigenvectors and eigenvalues. For 3D quantity, I am showing you another example. This is the 3D matrix. I am now importing. The next question was 3D quantity. This is the 3D quantity. Three-dimensional 3x3 matrix. We'll be assuming it as 1, and from our concept there are 3x3 identity matrix, and lambda will be used in the 3
by 3 matrix in this case. So I'm not going for the introduction, rather I'm going straight to the solution, how to take the solution of this one. The determinant of 5 minus lambda, 0 will be there, 0 will be there, 6, 17, minus 19 minus lambda, 0, 37 minus lambda, 23. Determinant of this must be equals to 0 in our case. And from there you will be achieving an the equation will be like 5 minus lambda. I'm not going for the details, you will be doing the details. And calculation is important here, remember, 37 minus lambda equals to 0. And from there, lambda values can be easily obtained as this. So these three are eigenvalues and corresponding eigenvectors. Okay, for lambda 1 equals to 5, say, what will it will become? The first thing, it will become 0. It will become 0. So the vector will be like 0, 0, 0, 6, 17, minus 19 minus 5, 0, 23, 37 minus 5, multiplied by, we can say, x1, x2, x3. In this case, 3 variables will be there. 0, 0, 0. From there, look, one thing here. There is no coefficient in x1 in any of these equations. So what we can say? We can just simply write down x1 equals to s, any value. It will not make any impact upon other values just because this 0 in all these equations. Okay, for lambda 1 equals to 5. Then what we get from the first equation, 6x2 plus 17 plus 17x3 equals to 0. In this case, okay, before we get to there, another simple solution is can be obtained here. This one multiplied this one, so it will be 32x3 equals to 0, which will give you x3 equals to 0. So x3 will be equals to 0. Then x2. So if x3 equals to 0, x2 will be again equals to 0 from this case as well. So you might ask me, okay sir, we are getting 0 values of variables, what will happen? Don't worry man, just because x2 is equals to 0, x3 equals to 0, but x1 is not equals to 0. We can use any values of x1 as s except 0. So we can say the s will be non-zero, as I have said, non-zero scalar value. So any value you can use as a s. So the corresponding eigenvectors will be x1, x2, x3, as we can write as, say, s 0, 0. So we can take common s here, 1, 0, 0. So it will be 1, 0, 0. We can also write. So whatever the value, this 1, 0, 0 is what I have said. This is nothing but the ratio. So whatever you use, if you use 1000 here in 1, 0 will be also multiplied by 1000, 0 will be also multiplied by 1000. So the basic thing is that it will always remain in this shape: 100, 500, 200, 300, minus 100, whatever it is. This is the eigenvector. The ratio of the vectors values is bounded within this vector. This is the corresponding vector of x1 equals to 5. So there is no other solution possible for this one, so you will getting this value. And I have said earlier that or at least one value. If it is non-zero, that is enough for non-trivial solution. Okay, for the next value, minus 19. For minus 19, the matrix will become like, it will be 24, 6, 17, 0, it will be 0, 23, 0, 0, and this will become 58. In this case as well, if I take this one, 58x3 equals to 0, you'll be simply getting x3 equals to 0. If you take the second, even if you take this value, you will get x3 equals to 0, just because x1 and x2 is absent here. And now the only thing, the first equation, if we take 21x1 plus 6x2 plus 17, x3 means 0, so this will be cancelled out, will be equals to 0. Now 24x1 and 6x2. So this is simply representing the ratio. So you can say let x2 equals to s. In this case, say s2 equals to s. So 24x1 plus 6s equals to 0, and from which you can obtain x1 value will be equals to minus 1 by 4s. So now we can write down the eigenvectors x1, x2, x3 as x1 is minus 1 by 4s, this is s, and this is 0. If we take common, this will be minus 1 by 4, 1, 0. So we can write the answer as minus 1 by 4, 1, 0. This will be the ratio. So you can also change the ratio as well. If we just multiplied 4 with this, it will become minus 4 with this one, so it will become 1, minus 4, 0. So this is also possible. So this is the ratio, actually, nothing else. So the ratios are bounded within the vector, that is the eigenvector. This is the corresponding eigenvector for lambda equals to minus 19, and lambda equals to 37. If we use lambda equals to 37, it will give us minus 32, 6, 17, 0, minus 56, 23, 0, 0, 0. So don't be afraid about why it becomes 0, 0, 0, 0, 0, 0, what also we have obtained here, but don't fear about that thing. Zero, 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 you can write here. From this equation, we'll not be getting any values. From this particular equation, we'll be getting values, say minus 56 x2 plus 23 x3 will be equals to 0. In this case, what we can do, we can assume s. So let x3 equals to s, we may assume. I'm again saying not necessary you will have to assume x3 equals to s. You can also use x2 equals to s. Whatever you do, the ratio will remain always the same in case of the answer what you will be getting. So don't be afraid about this. So minus 56 x2 plus 23s will be equals to 0, which will give you x2 value equals to 23 by 56 s. And if you use the first equation, minus 32 x1 plus 6 x2 plus 17 x3 equals to 0, and you put the values of x2 and x1 there, minus 32 x1 plus 6 multiplied by 23 by 556 s plus 17 s equals to 0, it will eventually become the value of x1 will be equals to 545 divided by 896, if I'm not wrong. This will be the value, and so the eigenvector we can write corresponding eigenvector of this one, we can write x, x1, x2, x3 equals to s, first 545 by 896 s and 23 by 56 s. Not necessary you will have to write this in this form. You can also use directly fractional form, point something, you can use like that, it doesn't matter. So we'll be taking common 545 by 896, 23 by 56 and 1, and as a result the answer will be this one. So you can use the convenient form. You can also make one to this one, you can make this one 1, or you can keep any values. So the main thing what I will be judging that your answer, whether after dividing this one with this one I am getting 23 by 56, or if I dividing this one with this one I am getting 545 by 896 or not. That is my concern. Whatever form you are taking the ratio, I will be judging and give you your result or marks based on that. So that was the thing for our class today. This was the content. So hopefully you have enjoyed. If you have any questions regarding this, you can ask. I will be trying to give you answer. Thank you.